Hello, my name is Magnus Petersen. This is my tutorial number 20 on TensorFlow, and this is about natural language processing. There's already a million tutorials and YouTube videos on this topic, but I found that I had to piece together the information from so many sources that I thought it might be useful for others if I wrote down my findings in this tutorial here. So the problem we will be studying in this tutorial is called sentiment analysis. And this will take us through a lot of the processing steps that are needed to work with natural human language inside a neural network. So in this case, we have a raw text. For example, this one here, this is not a good movie. And what we want to end up with is whether this is a negative or a positive sentiment. There are several difficulties in this. One of them is that the sequences may have different lengths. This is a very short one, but we will see examples of text that have more than 500 words. Another problem is that if we just look at individual words, for example, good, that indicates it's a positive sentiment, but it is preceded by the word not, so now it's a negative sentiment. And this can get a lot more complicated, and we will see an example of this below. But anyway, a neural network cannot work on raw text. So we need to first convert it into what is called tokens, and these are basically just integer values. So we go through our entire dataset and we count the number of times each word is being used. Then we make a vocabulary and each word gets an index into this vocabulary. So the word this has the integer ID or the token 11. The word is has the token 6. The word not has the token 21 and so forth. So now we have converted the raw text into a list of integers called tokens. The neural network can still not operate on this data because if we have a vocabulary of, for example, 10,000 words, the tokens can take on values between 0 and 10,000. And they may not be related at all. So word number 998 may have a completely different semantic meaning than the word number 9999. So what we do now is that we have what is called an embedding layer, and this converts the integer tokens into real valued vectors. So the token 11 becomes this vector here. The first value is 0.67, the next one is 0.36, and so on and so forth. And the next token, number 6, has this embedding vector here. And what we will see further below is that the mapping between tokens and embedding vectors learns the semantic meaning of the words, so that words that have similar meaning are somewhat close together in this embedding space. And what we get out from this raw text here is a two-dimensional matrix or tensor that can now be input to what is called a recurrent neural network, which can process sequences of arbitrary length. And the output of this network is then fed into a fully connected or dense layer with a sigmoid activation function, so the output is between 0 and 1. Where a value of 0.0 is taken to mean a negative sentiment and a value of 1.0 is taken to mean a positive sentiment. And what we have is we have a cutoff or a threshold value in the middle, so that values below 0.5 are taken to be negative sentiments and value above this threshold are taken to be positive sentiments. Now let's look a little more at the recurrent neural network because we haven't seen this before in my series of tutorials. And the basic building block of a recurrent neural network is a recurrent unit. And what I show in this flowchart is an abstraction of what goes on inside the recurrent unit. What we have here is the input, so this would be a word, for example, good, but of course it has to be converted to the embedding vectors, but we will ignore that for now. And the unit has kind of a memory state, and depending on the contents of this state and the input that we are seeing, we will update the state and write new data into the state. So for example, imagine that we have previously seen the word not on the input. We write that to the state so that when we see the word good on one of the following inputs, we know from the state that we have just seen the word not. Now we see the word good. So now we have to write into the state that we have seen the words not good together, so that this might indicate that the whole input text maybe has a negative sentiment. And the mapping from the old state and the input to the new contents of the state is done through a so-called gate. And how these are implemented differs from different versions of recurrent units. It is basically a matrix operation with an activation function, but as we will see in a moment, there is a problem with backpropagating gradients, so it has to be designed in a special way so that the gradients are not distorted too much. We will get back to that in a moment. we have a similar gate for producing the output. And once again, the output of the recurrent unit depends on the current contents of the state and the input that we are seeing. So what we can try and do is to unroll the processing that takes place with a recurrent unit. Now what we have here is just one recurrent unit, but the flowchart shows what happens at different time steps. So time step 1, we input the word this to the recurrent unit, and it has its internal memory state first initialized to 0. And this is done by Keras or TensorFlow whenever we start processing a new sequence of data. So we see the word this, and the recurrent unit state is 0. So we use the internal gate to update the memory state. And this is then used in type step number 2, where we input the word is. And now the memory state has some contents. There's not a whole lot of meaning in the word this, so the state might still be around 0. And there's also not a lot of meaning in the word is, so perhaps the state is still somewhat 0 in the next time step. But now we see the word not. And this has meaning for what we ultimately want to predict, which is the sentiment of the whole input text. So this we need to store in the memory. So the gate inside the recurrent unit sees that the state already probably contains near 0 values, but now it wants to store that we have just seen the word not. So it saves some non-zero value in the state. And then we move on to the next time step where we have the word a. And this also doesn't have much information, so it's probably just ignored. So it just copies over the state. And now we have the word very. And this indicates that whatever sentiment there is, it might be a strong sentiment. So the recurrent unit now knows that we have seen the word not, and now we see the word very. So it stores that somehow in its memory state. And in the next time step, we see the word good. So now it knows not very good. And it says, oh, this is probably a negative sentiment. So it stores that value in the internal state as some encoding in floating point values. And then in the final time step, we see the word movie, and this is not really relevant, so it's probably just ignored. And then we use the other gate inside the recurrent unit to output the contents of the memory state, and then it is being processed with the sigmoid function that we don't show here, and we get an output value between 0 and 1. And the idea is then that we want to train this network on many thousands of examples of movie reviews from the Internet Movie Database, where for each input text, we give it the true sentiment value of either positive or negative. And then we want TensorFlow to find out what the gates inside the recurrent unit should be so that they accurately map this input text to the correct sentiment. The architecture for the recurrent neural network we will be using in this tutorial actually has 3 layers. So it has recurrent unit 1 and 2 and 3. So in the first layer, what happens is what I just explained, except that now we need to output the value from the recurrent unit at each time step. Then we gather a new sequence of data, which is the output of the first recurrent layer. And then we can input that to the second recurrent layer, because recurrent units need sequences of input data. And the output that we got from the first layer and that we want to feed into the second recurrent layer are some floating point values that we don't really understand the meaning of. This has a meaning inside the recurrent neural network, but it's not something we as humans will understand. And then we do a similar processing in the second recurrent layer. So first we initialize the internal memory state of this recurrent unit to 0. Then we take the first output from the first recurrent layer and we input that, and we process that with the gates inside this recurrent unit. We update the state. We take the output of the first layer's recurrent unit for the second word is, and we use that as input, as well as the internal memory state. And we continue doing this until we have processed the whole sequence. And then we gather up all the outputs of the second recurrent layer, and we use that as input in the third recurrent layer, where we then do a similar processing. But here we only want the output for the last time step, which is kind of a summary for everything that it has seen. And then we output that to a fully connected layer that we don't show here. And then we have the sigmoid activation function. So we get a value between 0 and 1 out. And this is again our sentiment. There is a phenomenon called exploding and vanishing gradients, which is very important in recurrent neural networks. And let us go back and look at this flowchart here to explain what it is. Imagine that you have a text with 500 words, and we will have that in this dataset here. At every time step, we apply the internal gates in the recurrent unit in a recursive manner. So if there are 500 words, we will apply these gates 500 times to update the internal memory state of the recurrent unit. Now, the way that neural networks are trained is using so-called backpropagation of the gradients. So we have some loss function that gets the output of the neural network and then the true output that we desire for the given input text. And then we want to minimize this loss value so that the actual output of the neural network corresponds to the desired output for this particular input text. And so we need to take the gradient of this loss function with respect to the weights inside these recurrent units. And these weights are for the gates that are updating the internal state and outputting the value in the end. Now the gate is applied maybe 500 times. And if this has a multiplication in it, what we essentially get is an exponential function. So if you multiply a value with itself 500 times, and if this value is just slightly below 1, then it will very quickly vanish towards 0. So all the information in the gradient is lost by the time that we get back to this step here. Similarly, if a value slightly above 1 is multiplied with itself 500 times, by the time it gets back to here, it will have exploded. So the only values that can survive 500 multiplications are 0 and 1. They will remain the same. So the recurrent unit is actually much more complicated than what you see here. This is the abstract idea that we want to somehow map the internal memory state and the input to update the internal memory state and to output some value. But in reality, we need to be very careful about propagating the gradients backwards through these gates so that we don't have this exponential multiplication over many time steps. And I would encourage you to see some other videos on the mathematical definition of recurrent units, and I've seen a lot of them, and I don't think any of them were really fantastic. I think the best ones that I found were the ones from Stanford University. So you can find those on YouTube and have a look at those if you want a deeper explanation of how these recurrent units work. Okay, so now let's move on to the actual implementation. We need a bunch of imports as usual, and then we need to load the data. And Keras actually has functionality that can load this sentiment dataset from IMDB, but the problem is that it has already mapped all the words to integer tokens, and this is such an essential part of working with natural human language inside neural networks that I really want to show you how to do that. And also, if you want to use this code for sentiment analysis of whatever data you might have in some other language, you will need to do this yourself. So I have just quickly implemented some functions for downloading this dataset. And I actually think this dataset that I'm downloading here has twice as many reviews as the dataset used in Keras. So that's good, of course. Anyway, you can set another directory if you want to download it somewhere else. And the dataset is 84 megabytes. And it will be downloaded automatically with this call here. And then we load the dataset here. And as you can see, it has 25,000 text in the training set and in the test set. And let's just see one example from the training set. And it looks like this. This is a fairly short one. And the sentiment value is 1.0, which means it is a positive sentiment. So this is a positive review of whatever movie this was about. And now we get to the tokenizer, and this is the first step of processing this raw data because the neural network cannot work on text data. So Keras has implemented what is called a tokenizer for building a vocabulary and mapping from words to integer tokens. And we can say that we want a maximum of 10,000 words, so it will only use the 10,000 most popular words from the dataset. And we take all the text from the dataset and we call this function fit on text on the tokenizer, and it takes about 10 seconds, and then it has built the vocabulary. And it looks like this. So each word is now associated with an integer. So the word the has the number 1, the word and has the number 2, the word a has the number 3, and so on. And down here we see that the word movie has the number 17 and the word film has number 19. And what this all means is that the word the was the most used word in the dataset, and the word and was the second most used in the dataset. So whenever we want to map words to integer tokens, you will get these numbers here. Let's try and scroll down a little and take the word number 743, for example. And this was the word romantic. So whenever we see the word romantic in the input text, we map it to the token integer 743. So we use the tokenizer again to convert all the words in the text in the training set into integer tokens. So let's see the text from above again. We have it here. And when we have converted that to integer tokens, it becomes this array of integers here. So A becomes the number 3, symbol becomes the number 591, comment becomes 929, and so forth. We also just need to convert the test set to integer tokens, so we do that here. Now there's another problem because the sequences of tokens have different lengths depending on the length of the original text. And even though the recurrent units can work with sequences of arbitrary length, the way that TensorFlow works, all the data in a batch needs to have the same length. So we can either ensure that all sequences in the entire dataset have the same length, or we can write a custom data generator that ensures that the sequences in a single batch have the same length. Now it is a lot simpler to ensure that all the sequences in the dataset have the same length. The problem is that there are some outliers. We have some sentences that I think they are more than 3,000 words long, but most of them are only like a few hundred words long. So we would be wasting a lot of memory if we pad all the short sentences to have more than 3,000 words. So what we will do instead is we will make a compromise. First, we need to count all the number of words or the number of tokens in each of these input sequences. And what we see is that the average number of words in a sequence is about 221. And we see that the maximum number of words is more than 2,200. I said more than 3,000. Well, apparently it's only 2,209. But it's still a lot of words, and there's a huge difference between the average and the max. And again, we would be wasting a lot of memory if we just padded all of the sentences in the dataset so that they would all have 2,209 tokens. This would especially be a problem if you have a dataset with millions of sequences of text. So what we will do is we will make this compromise where we will pad all sequences or truncate the ones that are too long so that they have 544 words. And the way we calculated this was we took the average number of words in all of the sequences in the dataset and we added 2 standard deviations. And what we get out of this is that we cover about 95% of the text in the dataset. So only about 5% of the text in the dataset are longer than 544 words. So what we do now is we call these functions in Keras that will either pad the sequences that are too short, so they will just add zeros, or they will truncate the sequences that are too long, so it will basically just cut off some of the words in a given text if the text is too long. Now there's an important thing here, which is that we can do this padding and truncating in pre-mode or post-mode. So imagine that we have this sequence of integer tokens and we want to pad this because it's too short. Now we can either pad all these zeros at the beginning like here, so that we have the actual integer tokens down at the end here, or we could do it in the opposite way so that we have all this data at the beginning and then we have all the zeros at the end. But if we just go back and look at this flowchart here, remember that it is processing the sequence one step at a time. So if we start processing a lot of zeros, it will probably not mean anything, but because the internal state will probably just remain 0. So whenever it finally sees an integer token for the word this or whatever, it will know, okay, now we start processing the data. But if all the zeros were instead at the end, we would have started processing all the data, then we have some internal state inside the recurrent unit, but now we see a whole lot of zeros, so that might actually destroy the internal state that we have just calculated. And that is why it might be a good idea to have the zeros padded at the beginning. But the other problem is when we truncate a text. So if the text is very long and we truncate it, we cut it somewhere to get it to fit to 544 words or whatever the number was. Imagine that we cut this sentence here in the middle somewhere and it says now, very good movie, or this is not. You know, of course, we only do that for very long sequences, but it is possible that we lose essential information for properly classifying this text. So it is a compromise that we're making when we are truncating input text, and a better way would be to create a batch and just pad text inside that batch. So whenever we see a very, very long sequence, we pad the other sequences to have the same length. But we don't need to store all of this data in memory because most of it is wasted. We just do that per batch. And that's an exercise you can try and see if you can figure out how to implement that. Okay, so let's go back down. So now we have converted the entire data set so that it is truncated and padded. So it's one big matrix of data. For some strange reason, I cannot seem to find a function in Keras that maps backwards or has the inverse map from integer tokens back to text words. So we just need that here. It's a very simple helper function. And for example, the original text in the dataset was this. And if we use the helper function to convert integer tokens back to text words, we get this text out. And it's basically the same except for punctuation and other symbols. Oh, I see this is a movie about Jack Lemmon and Walter Matthau. Maybe this is, what is it called, like Grumpy Old Men or something like that. I think I would be a perfect character in this movie. I'm so grumpy all the time. I don't think I'm gonna be that in this tutorial, but some of my previous ones were a bit grumpy. Anyway. Okay, so now we get to the point where we have to create the recurrent neural network, and we will do this in Keras because it's very simple. So we do that with the so-called sequential model, and you should see tutorial number 3C if you don't know how to use Keras. And the first layer that we will add to this recurrent neural network is what is called an embedding. And I will go into more detail what this is further below, where we will analyze the output of this embedding. Let's go back and look at this flowchart here. So what we just did was we converted all the raw input text to integer tokens, but we still cannot input this to a recurrent neural network. So we have to convert that to so-called embedding vectors, which are values that are somewhere between -1 and 1. They can exceed it somewhat, but generally the values will be somewhere between -1 and 1. And this is data that we can then work on in the neural network. And this is somewhat magical because this is trained simultaneously with the recurrent neural network, and it doesn't see the raw words. It sees integer tokens, but it learns to recognize that there is some pattern in how words are being used together, so it can sort of deduce that some words or some integer tokens have similar meaning, and then it encodes this in embedding vectors that look somewhat the same. And again, we will analyze this in more detail further below. And what we need to decide is what is the length of each vector so that the token 11 gets converted to this vector here. And in this example here, we will use a length of 8, which is actually extremely short. Normally, it is somewhere between 100 and 300. And it's an exercise that you can try and change this number of elements in the embedding vectors and try and rerun this notebook and see what you get as a result. So if we go back down and look at the code here, we set the embedding size to 8, and then we use Keras to add this embedding layer to the recurrent neural network, and this has to be the first layer in the network. And then we can add the first recurrent layer, and we will use what is called a gated recurrent unit. Oftentimes you will see that people use what is called an LSTM, but the LSTM is, well, the authors of it say that it's a more general model and blah, 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 blah. But the evidence seems to suggest that the GRU, or the what I would call a group, because of I have a Danish pronunciation, I am Danish, but the group and the LSTM have similar performance on a wide variety of problems. And when you look at the LSTM, and again, I would encourage you to watch some of the Stanford videos for that, it has a clunky design. And it looks like there are gates inside the LSTM that are redundant. And indeed, the simpler group works just as well with fewer gates. You could add 1,000 more gates to the LSTM. It doesn't mean that it gets better. And there are actually recurrent units that are even simpler than the group. And some evidence seems to suggest that it performs even better than the GRO or LSTM, but it's not implemented in Keras, so we will just use the GRO unit here. And we say that we want an output dimensionality of 16, and we need to return sequences. If we go back and look at the flowchart here, we want to add a second recurrent layer. So we need to input sequences here so that the first layer that we have just added must output sequences. So we added the first recurrent layer here, we add the second recurrent layer here, and then we add the third and final recurrent layer here. And this one is not supposed to return sequences because the output here will be fed into a fully connected or a dense layer, which is just supposed to output one value for each input sequence. And this is processed with the sigmoid activation function, so it outputs a value between 0 and 1. And then we say we want to use the ADAM optimizer with this learning rate here, and the loss function should be binary cross entropy between the output here from the recurrent neural network and the true class value from the training set, which will be a value of either 0.0 or 1.0. And we can then just print a summary of what the model looks like. We have the embedding layer, the first recurrent unit, the second, the third, and the dense layer. And you will note that this doesn't have a lot of parameters. And then training the recurrent neural network that we have just built is very easy in Keras. We just call this function here. And this took about 22 minutes on my laptop with a GTX 1070 GPU. But because the neural network is so small, it actually only uses a small fraction of the GPU. So I think you could train this on an ordinary CPU in maybe, let's say, 1 hour. And then let's see how well it performs on the test set. And that takes a few minutes to calculate as well. And we get a classification accuracy of 86.71% on the test set. So that's fairly decent. This is a quite simple model, and you can try and tune all of the hyperparameters and see if you can get a higher classification accuracy, or you can just try and run more epochs during the training. These are all exercises for you to try out. So let's see an example of some misclassified text. So first we calculate the predicted classes for the first 1000 sequences in the test set. And then we take the true class values and then we compare them and we get a list of indices where these mismatch. So the classification was incorrect. And we see that there are 121 of these texts that were incorrectly classified. So this is 12.1% of the 1000 texts that we calculated here. So let's look at the first misclassified text. And it is this long one here. And I'm really happy to see that somebody out there on the internet is writing more text than me. Okay, I haven't read all of this. I just quickly browsed through some of it. And I think this is basically saying that the movie was really, really bad, but it was so bad that it was actually funny. So all of the words here seem to indicate a negative sentiment. And that is why our model has actually classified it as having a value close to 0.08, which is a very negative sentiment. But again, it's flipped on its head here because, for example, this text here, you never thought scenes of wanton destruction and general mayhem could be so unbelievably boring. But the character interaction is stupendous, the dialogue truly priceless, the incompetence on show somehow endearing. So it's flipped around. It's a really bad movie, but the person who wrote this super long review actually thought it was kind of funny. So they gave it a positive review, even though all the words here seem to indicate a negative sentiment. So misclassifying a text like this is probably okay for such a simple model that we have built here. But let's try it on some new data. So we have just created some data here. This movie is fantastic. I really like it because it is so good. The second one is just good movie. This third one is sort of neutral. Maybe I like this movie. I don't really know. The fourth one is meh from The Simpsons. You know, it means, this is probably not so good. Whatever. This one is kind of sarcastically negative. If I were a drunk teenager, then this movie might be good. So it has the word good, but all of this indicates that, you know, it's really not a good movie because I'm not a drunk teenager. I'm being sarcastic here. This one is very clear. It's a bad movie. This one is a negation like we've seen before. Not a good movie. It says it's a good movie, but it's not a good movie. So it's a negative sentiment. And this one is really clearly bad. This movie really sucks. Can I get my money back, please? So let's see if we can correctly classify the sentiment in these texts here. And remember that the neural network cannot work on this text directly. So first we have to use our tokenizer to convert it to integer tokens. Then we have to pad them so they are the right length. And then we can input them to the model. And the first one and the second one have been correctly classified as having positive sentiment, so value is close to 1.0. The third one was this one here, and the fourth one, and these were sort of kind of neutral, so we would expect them to be around 0.5. And these have been, the second one here has indeed been classified very close to 0.5. The other one here is somewhat negative. And this one down here has been misclassified. Well, it's unclear to the model what it actually is because it's very, very close to the middle. It is actually this text here. So it's not a good movie. It's confused about this. But this one here, bad movie, and this one down here have been correctly classified as having negative sentiments. Now, in all honesty, if you rerun this, you might get completely different numbers here. And sometimes it misclassifies even the obvious texts. So maybe the model that we have built here is not so good. Maybe you need, for example, more values in the embedding vectors. Maybe you need more values in the recurrent units, and so on. So this is all something that you should try and work with and see if you can get a consistently good performance on text that should be clear and obvious. Okay, so now let's look at these so-called embeddings. And if we just go back and look at the flowchart, remember that an embedding takes an integer token, such as this number 11 here, which is basically just the index for the word this, and then it converts the number 11 to a vector of floating point values roughly between -1 and 1. So let's try and analyze these embeddings. What has the model learned about what integer tokens might have the semantically similar meaning? So first we need to get the embedding layer from the Keras model. We do it with this function call here. Then we need to get the weight for this layer. And if we print the shape of these weights, you will see it's basically just a matrix. We have 10,000 words in our vocabulary, and we want each of those words to be mapped to a vector of length 8. So what this matrix basically just is a lookup matrix. So that once it has been trained, whenever we see an integer token for some word, we just look up the row in the matrix and say this is the embedding vector for that word. So let's try and get the token for the word good, which is 49, and let's try and get it for the word great, which is 78. And then let's look at the embedding vectors for these two words, or these two tokens rather. So the embedding vector for the word good, or the token for good, is this one here. And the embedding vector for the word great is this one here. The first element is roughly the same. It's 0.86 here and 1.07 here. It's sort of in the same ballpark. The second one, not quite. The third one also maybe not so similar. But this one here is again similar, and this number here and here is again similar. So some of them are similar and some of them are not. Now let's look at the embedding vectors for the word bad and horrible. So the first element here is somewhat similar to this one here, and this one here is also quite similar. This one here is not really. This one here is somewhat similar, and this one here is also. So again, we have the same, that some of them are quite similar, some of them are not. And what we can do is we make this little helper function here so that we can take one word and then we calculate, for example, the cosine distance or the Euclidean distance between this word and every other word in the vocabulary. And then we print the ones that are closest in distance and the ones that are furthest in distance. And if we call this helper function with the word great and use the cosine distance, then we have the words here that have the shortest distance. And of course, it has the lowest distance to the word itself. The distance is 0. And then we have some strange words here. Juliet, Ritter, the number 8, Elmer, nevertheless. I don't know. This doesn't make a whole lot of sense to me. But if we take the opposite end of words that are most dissimilar to the word great in this embedding space, then the embedding has learned that great and rubbish are very different words, and great and dull and disappointing and unlikable and uninspired and lax and worst and waste and awful and terrible. These are all very different words from the word great, that they appear mostly in different contexts. That is what the embedding has learned, and this makes sense. So now let's try the opposite, and we take the word worst. And again we see that the embedding has learned that, well, worst has a distance of 0 to itself, obviously. But here it has actually learned that there are very similar words. Embarrassingly, terrible, retarded, poor, stereotyping, uninspired, awful, severed, lax. And that these are all similar to the word worst. That they tend to appear in context with other words in a similar kind of pattern. And I think this is really cool that not only has it learned this from integer tokens, it just learns patterns between integer numbers, not even the words, but it does it at the same time as we are training the neural network itself. I think that's pretty cool. And anyway, words that have a great distance in the embedding space to the word worst are restrained and available and foremost and great and mesmerizing and highly and exploration and delightful and wonderfully and for some strange reason the number 7. And again, the embedding doesn't really have a deep understanding of what these words mean. It has just recognized patterns in the training data that certain integer tokens representing words have a tendency to appear in certain patterns, and that their meaning must somehow be related because of this. And this is sort of the general conclusion for this tutorial, that it's a clever way of doing pattern recognition. None of this has any deep understanding or human-like understanding of what the words and the text actually mean. It just learns to recognize that there are certain patterns that it has a tendency to mean that either it was a positive or negative sentiment in this text. And as usual, you can click on the link below this video to download this tutorial.